Hey there. So in the last video, we determined that if I have some particles in a box, right, and they're in line with each other and they can interact and bounce off of each other and all of that, we can treat the average force on one of the walls just like if the particles were all separate from each other and not interacting with each other at all, and we could just add up each of the average forces that they put on the wall, essentially. So for both of these pictures here, the average force on the wall would be as follows here: mvx1 squared over L plus mvx2 squared over L plus mvx3 squared over L. Right? So now that we've got that clear, we can basically mix and merge these two pictures together, right? And create a more complex scenario where we have a box of n particles. And we could generalize this result on for the force on one of our walls as basically m over L times the summation from I equals 1 to n of vxi squared. Right? That's just taking this guy where we have a small number of particles and we're converting it into a large summation where each of these particles has the exact same mass, m. If they had different masses, then of course, we would have to consider that and we couldn't use just a constant for m. In either case, L is always a constant because the size of the box is remaining the same. So, now that we're here, we just have to do a couple of simple manipulations to get to pressure. So the first thing that we're going to have to do, we know that pressure in a basic definition would be taking the force of something, dividing it by the area, right? So on one of these walls, right, the pressure on one of our walls, we can just say is F wall over the area, and the area is equal to L squared, of course. And so this pressure would just be m over L cubed times our summation from I equals 1 to n of vxi squared. All right. Another thing that we might want to consider is thinking about this little parameter, mass m, which is a very microscopic parameter. We might want to consider a more macroscopic parameter, for example, like the density of the gas, as opposed to the mass of each of the little individual particles. So to convert this kind of equation into that's not particularly difficult. All that we have to do is we know that density would be the total mass. So I'll just say m times my number of particles. So that would be the total mass of the gas in the box divided by the volume, right? And so what this tells us is that m equals v times rho divided by n. So that would be how we would convert our little mass in terms of density and volume. We're going to go ahead and plug that in. So we have v rho over n times 1 over L cubed, and then we have our summation term. And of course you go, so what is L cubed? L cubed would just be the volume of our box, right? And so these volumes are going to cancel out, and we're going to be left with the following. And I'm going to write this in a suggestive way. So I'm going to write rho times sigma from I equals 1 to n of vxi squared, and then this entire thing divided by the number of particles. All right, now we need to address the elephant in the room, which is basically this summation. And we can use a statistical definition actually to tackle this. Uh, and it's called the mean square. And I'll go ahead and use brackets like this to indicate that this is the mean of the velocity squared. So this guy here, I'll say is defined as sigma from I equals 1 to n of Vxi squared over n. So really, our pressure equals rho. Oh, and actually, let's be very clear about this. This is the square mean for our x velocities, right? We only have x directional velocities right now, so it would be rho times Vx squared, just like this. All right. Now that definition is probably, seems pretty random. So I think the best way to describe root mean square speed is just to jump straight into an example. So we'll go ahead and do that. Okay, say that I have 3 particles in a box. Go ahead and draw those particles out. And they're all going to have different speeds. Let's say that Vx1 equals 250 meters per second. Vx2 equals 270 meters per second. And let's say that Vx3 equals 195 meters per second. All right, now if I just asked you, find the average speed, find the mean speed, and I'll call this Vx in brackets like that, just the mean of the speeds, you'd probably, recognize to take the 250 meters per second plus the 270 meters per second plus the 195 meters per second, right? Summing up our speeds and then dividing it by the number of speeds or the number of particles, right? You take your the values of the data points, add them all together, divide by the number of data points, and that's going to give you the average. And so doing this, we would end up getting an average speed of, I think, about 238 and a third meters per second. So if that's how you would go about finding just the mean speed, right, the mean square would be very similar, right? I'm finding the mean of Vx, but squared, right? So this is pretty easy. You just think I would take my 250 meters per second squared plus my 270 meters per second squared plus my 195 meters per second squared, and then still divide by my number of data points. It's just we happen to be squaring each of our data points and adding them together. And so this happens to give me, I'll just round, about 5.7 times 10 to the fourth. That would be 5.8 times 10 to the fourth. Meters squared per second squared, because the squares also distribute into our units. So a little asterisk before I go any further with this is I'm kind of using the term mean square speed as like a filler term because you can clearly see by the units that taking the mean square of our data here is producing something that's not a speed. We're going to build up by converting this into what's called the root mean square speed, which is in fact an actual speed. It has units of meters per second. But yeah, anytime that I'm referring to mean square speed, it's not technically like a speed. It's the mean square of our data. So hopefully this example clarified a bit about what I mean when I say mean square speed, right? Again, this is just the summation notation for it. This is the exact, this guy right here is the exact same as this guy right here. If I were to put like a dot, 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 keep adding those terms together, and then this 3 is, n, like a lot of particles, however many particles that you're talking about. So hopefully this example made this term very, very clear. But I think another thing to consider for clarity would be to make sure that our units check out. So let's go ahead and check that out. So we're hoping to get a pressure, and we have a density, which has units of kilograms per meter cubed, right? And then we have this mean square speed, which has meters squared per second squared, right? And so we would get this cancellation here and have kilograms per meter second squared. And if you remember that a kilogram times meters per second squared, this is the definition of a Newton of force. And so we have a Newton times 1 over meters squared, right? Clarify for yourself that these terms are the same. Both sides of the equation here are the same. And so we have newtons per meter squared. Of course, this guy here is a force. This guy here is an area. We have a force over an area, which is what we would expect for pressure. Right, so I think it's always good to use dimensional analysis to make sure that our results are making sense. All right, so far we've basically addressed that this guy here is just the mean or average. This guy here is the mean square. But clearly this is not a speed, right? This has some funky units with it. So it'd be really nice to talk about something in reference to the mean square, but actually have things in terms of a speed. And so that's what the vrms is. So my root mean square speed for the x direction would be defined as just taking Vx squared, right, my mean square, and then just taking the square root of that. So for this example of the 3 particles, what would that be? Well, that would just be 250 meters per second squared plus the 270 meters per second squared plus the 195 meters per second squared all over 3, and then square rooting that entire thing. And this would be about 240.4 meters per second. Right, key point is that the root mean square speed is not the same as just your mean or average speed, right? Taking the mean square and then square rooting that does not get you the same deal as just a normal average. And there are lots of ways to prove that the root mean square speed will always be bigger than just the average speed. I'm not going to go into that in too much detail, but just recognize that these are all different definitions. So with that out of the way, we could write my pressure, which we determined was my density of my gas times my mean square speed. This could also be equal to the density of my gas times my root mean square speed in the x direction squared. Right? These are identical ideas. All right, so it looks like we've wrapped up our pressure. This is only the case when our particles have their velocity locked in the x direction, which is clearly not a very realistic scenario. The goal in the next video is going to be to think about when gases can move in 3 directions and see how that will affect this pressure. So with that, thank you so much for watching.